So last lecture I discussed about paramagnetic and diamagnetic materials, and we mentioned that for paramagnetism is mainly due to electrons just spin around its center, while for diamagnetism is mainly due to electrons revolve around the nucleus. In other words, it's really these atomic orbits that created this magnetic dipole that later create these magnetic macroscopic effects. And we also mentioned that for this kind of materials, the magnetization is really sustained by the external field that we applied. So if the external field B is removed, then this magnetization also just disappear. So for most of the materials, the magnetization is actually proportional to the B field that are applied. Okay, of course, if that magnetic field is not too strong. Okay, so what we do is we often define this magnetization, okay, is proportional to the H here. Okay, so where this chi m, we call it magnetic susceptibility. Okay, because m is proportional to H. And then we know that B is really defined as mu 0 times H plus M. Okay, so what do we have? If you plug in, this is really mu 0 times 1 plus chi M H. Okay, so if you add this, plug this into this formula, so we can define this as mu. Okay, which is really, what do we call it? Sorry. We call it as the permeability of the material. Okay, so in the vacuum, for the vacuum, we have chi m equals to 0, and then we have this mu is really equals to mu 0. So in other words, that this mu 0 is really the permeability of free space. Okay, and this chi m can be positive and can also be negative. So you can see that for paramagnetic material, it should be positive. It is greater than 0 for this paramagnets, and this one should be less than 0 for this diamagnets. Okay, so this is just this is something we call the linear media. Okay, because the magnetization is really just proportional to H, and H you see here is proportional to B. So in other words, that M is really proportional to the external magnetic field applied. Okay, now let us consider a simple example. Okay, so this is similar to what we did it before when we talk about the magnetostatics. So let us consider an infinite long solenoid. So there are n turns per unit length, and there are many wires that are wired around. Okay, and there are current I that are flowing through the wire. okay, and this is the z-axis, okay, and this is a solenoid, okay, and there are n turns per unit length. Okay, so let us say this solenoid is now filled with linear material of susceptibility of chi m. Okay, so we want to figure out what is the magnetic field inside this solenoid. Okay, okay, so you know, of course, we wanted to figure out what is the B field inside. Okay, and now that because of the magnetization, so it's difficult to figure out this M first. Okay. Okay, but what we can do is we can still use this Ampere's law. Okay, because Ampere's law is really with the magnetization considered. We have this H dot dl to the integral is equals to the amount of current that are included, inside the Ampere loops that we defined. So what we can do is, we can define a small Ampere loop, that is look like this way. We can define the length to be L, and we know that for the solenoid field, the field that outside is really equals to 0. Okay, so and we know that the magnetic field should along this z-axis. Okay, so if we have this, so this is really h times this length L. Okay, it's really only along this one the magnetic field is non-zero. All three other edges, they should equals to 0. Okay, so this one should be equals to this Ni. Okay, because it's per unit length, then times L. Okay, from there, we have H is really equals to Ni, and we know it is along the z-axis. Okay, so we kind of get this H value. Okay, so now because this is a linear material, okay, so if we know that B is just proportional to H, so now we have H, so we can easily find the B. Okay, B is just really mu 0 1 plus chi m H. Okay, which is the really mu 0 1 plus chi m Ni along the z-axis. Okay, so that is really what we have. Okay, so of course, so from here, of course, we really can calculate M. Okay, because M is just chi m times H. We can also get M is really equals to chi m times Ni along the z direction. Okay, so once we have this, we can also calculate the bound surface current. Okay, you have to remember that the formula that we used to calculate the bound surface current is really M cross N hat. Okay, so which one, is of course, along the surface of this solenoid. Okay, so from here you see that this is chi m times H times N hat. Okay, and from here that we know H is really along the z direction. H is along the z direction, and this N hat is really along this radial direction. Okay, so H times this N hat, we are pointing along this phi direction. Okay, so in other words, that this is really chi m, H is really Ni, so this is along the phi direction. Okay, so now you see that this is really, as I said, this is a boundary surface current Okay, so you can see that we also said the wires can also be kind of treated as a current, which is really Ni. Okay, there are N turns per unit length, and each one carries a current I. So in other words, that there is already a surface current that is Ni. Okay, now because of the magnetization, and it also created this boundary surface current that is also along this phi hat direction in the same direction as this. Okay, so this one you can see that this is same direction as the current. What do we have here? N times I. Okay, or n times I, depends on what you wanted to calculate. So if this one, if chi m is greater than 0, it is the same direction. Okay, so that really means it will increase the induced magnetic field. So in other words, it is a paramagnet. Okay, and of course it will give the opposite direction. Okay, as the current that we applied, on this wire. So of course, it will be opposite direction if chi m is less than 0. Okay. So here just to show you, you know, you see that the most important one is really to use this Ampere's law. Okay, for things that we have magnetization. Okay. The good thing is really, here is you only need to worry about the free current, and you don't need to worry about this boundary surface current, and also boundary volume current, which are often difficult to calculate. Okay, so now I want to talk about the last section, about this magnetism, in material. Okay, so this is about the ferromagnetism. Okay, and we talk about paramagnetism. We said is because the electron just spin, and that cause current, and we can treat it as a tiny magnetic dipole, and we can calculate, it will cause magnetization for material. And we also talked about this diamagnetism, where is really the electrons revolve, around the nucleus, and then you can also treat it as a, slightly bigger magnetic dipole. And we also can calculate the effects, on the magnetization and also the magnetic field. Ferromagnets, is different from the paramagnets and also the diamagnets. So, as I described before, paramagnets and also diamagnets, they are sustained by the external magnetic field. If the external magnetic field is 0, and then the magnetization will also becomes 0. But ferromagnets is different. Okay, it doesn't require to have external fields to sustain the magnetization. Okay, so that is very different. It took many years, for us to really understand, what caused this ferromagnetism. Okay, so what happened is, like paramagnetism, ferromagnetism also involves the magnetic dipoles that are associated with the spins, of these unpaired electrons. Okay, so the only difference, the new feature is really there are interactions between the nearby dipoles. You can see that two electrons, each one will spin around, create a small magnetic dipole, and the two electrons, they are nearby. Okay, so they will strongly interact with each other due to these quantum effects, that I couldn't really describe all the details here. Okay, but what happened is, for this ferromagnet, each of these dipole, they likes to point in the same direction as its neighbors. Okay, so that is the difference. Okay, this is really the interaction between nearby dipoles. Okay, okay. So what happened is, each electron, they like to point in the same direction as its neighbors. So then you can see that there are many electrons. Their alignment, they are close nearby, and they point into the same direction. Okay, so the thing is really this kind of alignments occurs in relatively small patches. We sometimes call domains. Okay, so each domain, kind of, there are billions of electrons. Each one create a dipole, and they all line up in the same direction. But these small patches, there are many domains. Each domain, they are kind of randomly oriented. Okay, so in other words, at the very beginning, from the macroscopic effect, is really there are no magnetic field from that material. Okay, so now what happened? Okay, now if we put a piece of this ferromagnets into a strong magnetic field, so as we learned from this paramagnetism, then there will be a torque, applied on each of these magnetic dipole that are created by the electron spin. So this torque will tends to align the dipoles, parallel to the field that we applied. Okay, so of course, since as I described, the electrons like to stay parallel to their labels. So in other words, most of these dipoles will really resist this torque. Okay, so it will really still keep the original alignment, and will not align the dipole parallel to the field. However, at the boundary, between two domains, there are also competing neighbors. Okay, between inside the label, okay, they still like to stay parallel to their labels. But let us consider the boundary between two domains. Okay, so in other words, that we have this torque, they will make some of these electrons, close to the domain. Okay, will make it parallel to the field. Okay. Okay, so in other words, that you can see that the net effect of this magnetic field is really to move the domain boundaries. If you apply it, okay, then there are some domains. They have the inside that domain. Okay, all electrons just happened parallel to the electric field. So in that case, after you apply another external field, this domain, okay, that is parallel to the field will grow. Okay, so that means other domains, of course, will shrink. Okay, so you can see that if the field is strong enough, okay, at the end we will have one domain that takes over entirely. Okay, and then that material, we often say it becomes saturated. Okay, okay. So now, I kind of wanted to describe you this process. So let us say I have some material here. Okay, let us say it's some iron, for example. Now we wire some, we put some wires on it. Okay, we do it. We put some wires, and we have some currents that flow through the wires. Okay, and we know that it will create a magnetic field that will pointing to the left. Okay. Okay. So now we just see that if so let us make a plot. Okay. So we make a plot. The x-axis is the current we applied, and the y-axis is really the magnetization. Okay. So what happened is, now let us say we run a current through this wire. Okay. And as I said, it will create a magnetic field that pointing to the left side. Okay. So now if we increase the current, okay, then the field will increase, and then we said the domain, that have electrons, aligned to the external field, they will increase. Okay, they will increase, and then this material becomes, magnetized. Okay, now, if it continues to increase, okay, will increase. Okay, then of course, as I said, after the electric field becomes very strong. Okay, and then we have the whole material we are dominated by one domain. Okay, so all the dipoles, they are aligned in parallel to the magnetic field. So a further increase, in current will have no effect on the magnetization. Okay, so let us say this is the point A, so this is the point B, where we said that it is already, this is the saturation point. Okay, now let us assume we reduce the current. Okay, so now you will find that instead of retracing the path, okay, you will think that if we reduce the current, then the magnetization will becomes smaller, and then go back to zero. Okay, so actually what happened is, for this ferromagnets, instead of retracing the path, back to this m equals to 0, so there is only a partial return, okay, to these randomly oriented domains. Okay, so what happened is I decreases, and it will m also decreases. Okay, but it doesn't follow the original path. Okay, so now when this I is now equals to 0, and you can see that there are still some remaining magnetization, okay, at this point C, and you can see that now this material, becomes a permanent magnet. Even there are no external magnetic field applied, it still contains some magnetization. Okay, so now if we want to eliminate the remaining magnetization, so we have to really change the current. Okay, change the direction. Originally is this direction, now we change the current direction, then it becomes negative. Okay, so negative, so now we can run a current that is backward through this wire. Okay, and we continue to increase this I, and then you see that after that, it really the magnetization just disappeared. All these directions, domain alignment directions becomes totally random. Okay, so now if we continue to increase the current. Okay, we are of course we are get to saturation point again. Is just like what we have here. It's just in a different direction. Okay, so current the magnetic field is big, and then the magnetization becomes bigger, and there will be one domain that will dominate, and all these magnets at some point will be all lined up to this to the right side direction, which is the new magnetic field direction. And then if you further increase the current, it will not help. Okay, so then same thing, if we go back, okay, it will not go back to this path. It will go a different path. And same thing when you go back, when current is zero, and you still have some magnetization that remaining there, and then you can change the current direction again in order to get rid of this remaining magnetization. And then if you further increase that at the end, you will get to the saturation point again. Okay, so this is you can see some curve like this. Okay, so this kind of curve is called hysteresis loop. Okay, and what you can see from here, that the magnetization depends not only on this applied current. Okay, when current is different, and they are different. Okay, but it also depends on its previous magnetic history. So you can see that especially when we have zero field, zero current applied, and you can see that it can be in three different situations. Depends on its previous magnetic history. Okay, and you can also see from here, for this case, if the current is really equals to zero, and we still have magnetization there. Okay, so in other words, these 2 points really indicate this object is really a permanent magnet. Okay, so this is just wanted to introduce you this ferromagnetism. The real effect is very complicated. You have to learn pretty advanced quantum mechanics in order to understand the interactions between different between neighboring electrons. Okay, but here just tell you give you a rough picture about the ferromagnets. Okay, and how we can get some permanent magnets. Okay, so this is all I wanted to talk about for this chapter. The magnetism inside a material. Okay, so as you can see that this is very similar to what we had before. Talking about the electrical field in inside a material. We have the magnetization, and this magnetization, you can treat it as really bound surface current and bound volume current, and we can really calculate this. And we also introduced the edge, for example, that only depends on the free current, so that it will be easier in many cases for us to do the calculation, since the bound currents are often difficult to calculate. Okay, so far I think I already finished 2/3 of this course. We talk about magnetostatics, and we talk about electrostatics. So now I wanted to talk about a new chapter, okay, which is called electrodynamics. Okay, so far, we only studied, the electric field and also the magnetic field that are caused by stationary charges or steady currents. Okay, the charges are stationary, the currents are really steady. So we only the first case we only talk about the electric field, and for the current case we talk about the magnetic field. Now we really want to study the effects where the electric field and the magnetic field, they depends on time. Okay, and later you will see that we really know that the these two fields actually they are really just one field. We call it the electromagnetic field. Okay, and we will mainly talk about three important pieces. So we will first talk about the electromotive force, and then we talk about electromagnetic induction. Okay, then at the end, we will introduce Maxwell's equations. Okay, so these are really just three, some sections. Okay, we will discuss for this chapter. Okay, so we will first talk about the electromotive force. Okay, so the first one is really the Ohm's law. Okay, I think most of you already know that is, you often write it down as V equals to I times R. Okay, but now we're talking about something slightly different way. It's a different picture, but at the end I will show you this, the more standard formula. Okay, for Ohm's law. So what I talking about here is, we have the charge. Okay, so we need to have some force, that are applied on this charge, in order to get a current flow. Okay, okay, so you can see that the current density. Okay, okay, it's really equals, it's proportional to the force that are applied. Okay, so this is, let us say, is really the force that are per unit charge. Okay, let us consider this. Okay, per unit charge. So in here Q is really equals to 1 here. Okay, so the current density should be proportional to the force that we applied on these electrons, in order to have the electron move, that will electron or some charged ion or whatever, is some charges. Okay, so we have to have force applied on the charged particles in order to get current flowing. Okay, so for the most material, as I said, the current density is proportional to that. Okay, so let us consider the the factor is really called sigma. Okay, I know that many of you will think that this will be the surface charge that we described before. Unfortunately, we are short of symbols here. So this sigma is not really the surface charge we described before. This is really the conductivity of the material. Okay. Okay. So for different materials, this conductivity, will be different. Okay, So you can see that if some material, if if sigma is really large, okay, so that really means is if there are some small force applied on it, okay, and it can sigma times F will be big, the current density is high. Some material, so that means it is more like a conductor. There are some materials where sigma is really small, okay, so you need to have a lot of force applied on the charged particles in order to create some currents. So that is more like insulators, okay. Okay, so this is the conductivity, and we also define a variable resistivity. Okay, so here unfortunately people also use this rho, okay, to indicate the resistivity. This is not really the volume charge density that we used before. Okay, okay, and from here you can see that rho is just equals to 1 divided by sigma. Okay, you can see from the name, one is conductivity, one is resistivity. They are really opposite to each other. Okay, so now let us consider for a perfect conductor. For perfect conductors, okay, the resistivity is 0, okay, the conductivity is really infinity, okay. So very small amount of force applied on the charged particle can create a huge current density, okay. Then of course we also have for the perfect insulators. For this one, rho is really infinity. The resistivity is very very big, okay, and the conductivity is really equals to 0, okay. So this is what just to introduce the conductivity and also the resistivity, okay. And as you know that for these metal materials, they often have very small, metal material, let us say, metal material, like a silver, like copper, like a gold. We know that they are very iron, okay. So they often have very good conductivity. So the resistivity, is really small, and resistivity is something like conductivity, resistivity is around 10 to minus 8. Okay, it's a small number. But, for something like seawater and for germanium, these are semiconductors, diamond, they have resistivity, for these semiconductors. So they have rho, that are close to 1. Okay, while for insulators, like pure water, okay, rho is around 10 to with of 3. Okay, so this is the water, okay, and this is for pure water, okay. And then if it's glass, is the value is a range, 10 to 9 with the power 10 to 14, okay. And it's around this level. This is something for glass and for rubber, okay. It becomes insulators, okay. Different materials are different, okay. Okay, so here of course so far when we talk about this Ohm's law, okay, J is really equals to sigma times F, okay. And F of course is the electromagnetic force that are applied. So we have so we because we are talking about so this F, because we are talking about the force applied on the unit charge. So this should be E plus V cross B. Okay, so this is the force that due to electric field, due to the magnetic field. Okay, and because E is really equals to 1 here, we are talking about the unit charge here. Okay, so F is really E plus V cross B. Okay, so in other words, that J is really sigma times E plus V cross B. Okay, and for the most cases, the V is often a very small number. Like if we are talking about the conductors, the electron speed. Okay, electrons, they are current flowing through. Electrons move around, but the velocity is only about 1 centimeter per second. So it is really a small number. So this V is often small. Okay, so as a effect, this V cross B is really much smaller than E. Okay, so in other words, that this J is almost proportional to this sigma times E. Okay, so this is really another way we see it. This is really Ohm's law. Okay, equals to J equals to sigma times E. Okay, I mean this is also Ohm's law. Okay, I mean I just write down F is F is really so this one is really a special case, where this force is really the electrons are not really moving that fast. Okay. Okay. And now let us consider, we know that for an ideal conductor, ideal conductors, we know that from the electrostatics, and we know that there are no really charge that are inside the conductor. Okay, so in other words, that E is really equals to 0. It's inside. There are no, net charge. Okay, that are inside the material. Okay, so as a result, the E is equals to 0. So that really means there are no, current flowing, inside. Okay. Now we will show you that for the perfect current, okay, for the perfect conductor, because this J is really sigma is really big. Okay, because for a perfect conductor, the conductivity is really equals to infinity. So we really see that this one E also is 0. Okay, for perfect conductors, even though this time we really have current flowing. Okay. Okay. Current flowing, there are also no electric field there. I mean, you can think about that because they are perfect conductors, electrons can almost move without leading the electric field applied it. Okay, and you can have the current that are flowing around. Okay. Okay, so now let us look at now I want just to show you to the more normal format of this Ohm's law. Okay, let us consider a wire. It doesn't need to be wire, it can be any shape. Okay, so there is the area. Okay, let us say is A. Let us say this length is L. Okay, and there is a current flowing through. Okay, and let us say if I assume the voltage difference is V here. Okay, and we also know the conductivity of the material is a sigma here. Okay, now we want to figure out what is really the current that are going through this wire. Okay. So the current, the current is really the current density times the area. Okay. Okay. And we know that the current density, the due to Ohm's law, okay, J is really proportional to sigma E, the electrical field there, okay, times A, okay, and the electrical field is really, in some sense, is really this V divided by L, okay, so the length, the voltage difference is V, and the length is L, okay, so we have V divided by L. So you can see that, so this is really sigma A divided by L times V, okay? And you can see that V and I, they are proportional to each other, okay? We can, like what we did before, we can figure out what is the resistance, okay? The formula that we often used for Ohm's law, which is really V equals to I times R. Okay, we can calculate the resistance, okay, which is really L divided by sigma A. Okay, so this is for a wire that have any shape, okay, and the cross section for this wire, is A, and the conductivity is sigma. Okay, so this is how we calculate the resistance of this wire. Okay, now let us look at another example. Okay, so now we have have two cylinders. Okay, they are coaxial. Okay, so it's like this. Okay, so one has a radius of A, the other one has a radius of B. Okay, and their materials. Okay, that are between these two each one is a metal cylinder, okay, and there are materials there that have a conductivity that is sigma, okay, and these two wires, these two cylinders, they are maintained, okay, with a voltage difference of V, okay. Now we wanted to figure out, what is the current, okay, and that are flowing through from this point, between the two cylinders, okay, and we also wanted to figure out, what is the resistance, okay, for this, okay. In order to do this, okay, so what we really wanted to do is, we know. We needed to figure out the electrical field, for example. So what we basically idea is we first, we needed to find the current. Okay, current we know is related to the J. Okay, to the current density. Okay, and this current density, according to the Ohm's law, is really related to E, okay, the electrical field there. And we also know that the voltage difference is also related to E, okay. So in some sense, we wanted to first figure out the E, and then go back to find the current, find the voltage, okay. So to do that, we can assume, if there is a charge that are per unit length, on this inner cylinder. Okay, so what we can do is, we can, like what we did before, we can define a Gaussian surface. Okay, that is slightly bigger than the inner cylinder, and we can use the Gauss's law. Okay, we can figure out the electrical field there. Okay, this you already learned that before. Okay, so I will not really do the calculation again, but it will be 2 pi epsilon 0 S hat, okay, where S is really the distance away from the central axis, okay. So this is the electrical field that we have, between the two cylinders, okay. So now what we do is we first figure out the current. As I said, the current is really the current density times the area, okay. Then we do the integral, okay. And we said that this J is really equals to E dot A. J is really sigma times E, okay. And we know that the sigma, okay. So this integral, we know that we are talking about also another cylinder here, okay. Cylinder here, and let us assume the length is L, or you can let us just use this volume, the length there, okay. The magnetic okay, let us use this small Gaussian surface that I discussed. Let us assume the length is L, okay. So it's just and we know that the electric field is really uniform, for the is the same for giving S value, okay. So what we do is the field is this, the electric field is this, the area is really 2 pi s times the length, which is L, okay. So from here we can have so 2 pi s cancel, so we have sigma divided by epsilon 0 times lambda times L, okay. So this is how we figure out this current is related to the E, okay. And then the same thing we said, this voltage, okay, is really, go back, this is the integral of E dot dl, okay. So this is what we discussed in the magnetostatics. So from here you can do the integral, okay, and this is S. If you integral, it becomes log S, okay, and you will find this is lambda divided by 2 pi epsilon 0 log B divided by A, okay. So this is what we have, okay. So this is we calculate V, okay. So for the current, there is still nominal we don't know, okay. So I mean, in principle we solved this problem, but we don't know what is the nominal, okay. So the nominal is really, you can see here, is related to V, and from here we can calculate the lambda. It becomes 2 pi epsilon 0 divided by log B divided by A times V, okay. So this is kind of the charge per unit length, okay, on this inner cylinder. So once we have this charge per unit length on the inner cylinder, we can just plug in here. We can get the current becomes sigma divided by epsilon 0, 2 pi epsilon 0 log B divided by A times V, okay. And you can see that this is really I need to times lambda times L, okay. So there is another L there. So this one becomes 2 pi sigma L epsilon 0 cancel divided log B divided by AV, okay. And from here you can also see that V is proportional to the current, and we can get the resistance, okay, which is V divided by I. So it really becomes log B divided by A divided by 2 pi epsilon sigma L, okay. So this is the resistivity of this this kind of configuration, okay. There are two metal cylinders, and there are some materials, that with different conductivity there. You can think about the normal wire we have, you know, there are current flowing through, and we often put the rubbers, around the wire, for example. Okay. So now, we also calculated this capacitance before. Okay. So you have to go back, look at the lecture note that I gave before when we discuss about the capacitance. Okay, and you will find there it is really 2 pi epsilon 0 divided by log b divided by a times l. Okay, so it's like that. And then you can really find, just for fun, you can calculate r times c, and you will see that it really becomes sigma 0 divided by, so this is r times c. Okay, so L, all they cancel with each other, so it becomes sigma 0 divided by epsilon 0 divided by sigma. Okay, so this is just for this kind of material we have this pattern. Okay, that's all we want.